Now, there is a well-developed theory of affine transformations with Cartesian coordinates, homogeneous coordinates actually, by multiplying vectors and matrices. That's fine, but here are some special cases that are handy to have at the ready. First of all, if you rotate the vector xy by 90 degrees counterclockwise, then you get minus yx. If you multiply out the appropriate rotation matrix, this is also what you get, of course, but it keeps things simple to know that it's really just a swizzle and a minus sign. And it's obviously linear. Rotation by a variable angle is not a linear transformation, but rotation by a fixed angle is. It's just that 90 degrees is like extra simple. Let's talk about the dot product, or inner or scalar product. It's just the sum of the component-wise products, simple enough, but it has some nice geometry too. A dot B equals the length of A times the length of B times the cosine of the angle that they make. So, assuming the vectors are non-zero, their dot product is zero if and only if A and B are perpendicular. It's positive if they point in the same direction and negative if they point in opposite directions. You can even get some more geometry by normalizing one of the vectors, say B. Then its length is 1, and what we're left with is length of A times cosine alpha. That's the length of A projected onto B. This can be pretty useful, and again, for fixed B, it's linear. Finally, very briefly, there's the cross product or outer product. I'll ignore other dimensions because it gets a little bit funky, but in 3D, it's super useful. Given two vectors, it gives you a third one that's perpendicular to both of them, and its magnitude has a useful interpretation too. Look it up, and while you're at it, check out why there is a left-handed and a right-handed version.